Zurier from Classical High School in Providence, who won second prize in the Siemens competition. In my humble opinion, should have won the first prize when talking about the joints problem. Anybody who wants to join us for dinner, let me know as usual place. It's 6:45, right after the talk, when you can make it. Thank you.
So, I worked on a problem called the joints problem. That's what we're going to be talking about today. So the joints problem is a problem in incidence geometry. And people are probably pretty familiar with that sort of thing. But the kind of problems you worked on are like, I guess this is kind of a sort of celebrated zero. The Severetti problem. And so this basically says, if you have some collection of like endpoints, and you have some lines, and it says that the number of instances is like, I don't know, it's something like this. I think there might be some special cases, but basically, it's all about you have some points and lines and maybe some other like simple objects, and you want to count them. So geometric combinatorics. So the joints problem is a problem in the third dimension. But to introduce it, I'll do a simpler problem.
So what's n and what's n again?
N is the number of lines, m is the number of points. Okay. So do a simple problem in the plane. So if I have n lines, what is the maximum number of intersections? So we'll define an intersection as just any line meeting another line. So this only counts as one intersection, because otherwise we could just put them all through this one point and it wouldn't be very interesting. So what's the maximum number of intersections that we get with n lines in the plane? And choose two. Because if none of them are parallel, everything will intersect each other, so it's very easy. Okay. So in 3 dimensions, we'll say it's still not very interesting because we put them all into a plane. So let's do. So instead we'll say a joint is going to be, you take 3 lines off to intersect at a single point, and they can't line in a common plane. So their tangent vectors have to span R3. So the question is, if we have some number of lines, n lines, then we can have a function, f of n, that says, consider all the configurations with n lines, which one has the maximum number of joints. And so we want to study this function. Okay, so some small cases of this. With 0 lines, we'll only do table 3. So we'll see how far I get. N lines. So these first few are easy.
0.
Okay, so what's this one?
1. Okay.
This one? It's also 1, because there's no way to do that. This one's 2, because you can do like that. Okay. Oh, this one. 3. Okay. You drink 4. Yeah. So. Okay. So you can do 4. Now. After this, it gets really hard because it's not really easy. Okay, so these are my best guesses.
So it is in the OEIS, online encyclopedia. It is sequenced in the so-called OEIS, online encyclopedia.
No.
So it should be.
Maybe I'll submit that. It might be. Okay. This one's also 4, I think. This one you can do 5. With 9 you can do 7. And I won't drag that one because it's really nasty.
And 7 is optimal?
I'm not sure that 7 is optimal, but I'm pretty sure it is, and I'm positive that this is optimal. there's a really nice configuration for 10. But what's becoming clear is that we can't do this for small cases. It just doesn't work. It's like very computationally intensive, and there's a lot of cases. So we'll go straight from like 10 to infinity. We'll say so f of n. What's a good? Can someone think of the upper bound for f of n? Just a stupid upper bound.
N cubed.
N cubed. Sure. I was thinking more this, because if everything intersects each other 3 times, then every intersection necessarily contains a double intersection. And if every line intersects each other, we just showed it was n choose 2. So it's still n choose 2. And by the way, if we want a lower bound, then I think this works, because you can do like that, or however. Okay. This is really hard to beat and choose 2. And we're going to need to choose some harder things to beat it. But first I want to focus on the lower bound, because that's a little easier. So to find a lower bound, all you have to do is arrange some joints in like a clever fashion. And then you can count them. So who has an idea for a good way to arrange joints? Okay.
You could build on the simplex idea.
We could do the simplex.
I'm not sure if that would generalize.
It would generalize. I mean, well, what do you mean? You can make like just a large tetrahedron, but like connect all the
Oh, you want
parts.
not three.
You can do that. But it'd be simpler to just do like cubes. Just like this. Okay, so this is obviously worse than some of these because it takes 12 lines, we're only at 8. And I claimed that there's an example of 10 lines that make 10 joints. But you can do this, it's very easy to extend. So you can just say if we have n, we'll say we have k cubed, or L cubed points on a cube. And then how many lines do we need to determine them? So it's L squared from this direction, and from there. So 3L squared points, lines. So if you solve for L cubed in terms of 3L squared, you get like this as a lower bound. Okay. You can do a little better than the constant, but this is the best exponent. The way you do the constant is you consider m planes in general position, and then so every m choose 2 intersects each other. So every pair intersects each other. So there's n choose 2 lines, and every 3 tuple intersects at a joint, and you can check that it spans, and it works. So this means that there's like m cubed over 6, which is close enough for, like, we're dealing with infinity, so we don't need to worry about the small order terms. M cubed over 6 equals the number of joints. M squared over 2 equals the number of lines. And I'm going to do it the algebra because I want to find out the constant. So this means that joints is 2L 3/2 over 6. And so the constant is square root of 2 over 3? That sound right? I think that's it. Okay. So joints is square root of 2 over 3 times the number of limits. 3/2. So that would be our lower bound here. That's the best we can do. And this is the conjecture of best lower bound, the square root of 2 over 3 into 3/2. So now the upper bound. So this was introduced in like 1990 something. And they have a proof of the upper bound as big O of n to the 7/4. And it's really complicated. So it uses some properties of algebraic surfaces, something called a regulus, which is, don't worry about it, it's like a ruled surface. And then a lot of like really smart people worked on this. Like I know Terrence Tao worked on this, and he got like into the 1.6 something. So it's a hard problem. But a few years ago, a new technique was introduced by Larry Guth, and it's called the polynomial method. So I'd like to talk a little about that. The polynomial method is motivated by, if we have, I need the proof for this, but it's a little bit involved. So we have key points. In k dimensions. I guess this works actually for f to the k, whatever. We're doing geometry, so we'll just do r to the k. And there exists some polynomials of k variables. Such that p, so these p points, so they're all k tuples, right? So we'll call them y1, y2. And each of these is a tuple x1, x2 to xk. So there's just some polynomial that the polynomial is not zero polynomial, but it vanishes on all the points. And so the question is, do you believe me that I can find such a polynomial, first of all? And I think that should be, what?
Wait, you're in RK, you want to find it that vanishes on k points, it's not zero?
Yes.
It's uniquely determined by what it does to sort of k points.
No,
This is n variable. It's a k variable polynomial. It's a polynomial of k variables.
Oh.
Okay. So, where was it? So I think it's pretty easy to say that there exists some polynomial that works, because we can just do like x1 minus the first coordinate of this first point times x1 minus the first coordinate of the second point, and so on. So then there's a polynomial. What we should be concerned about now is the degree of this polynomial, and the minimal degree.
Sorry. Can you just say that?
Yeah, sure.
Again? Yeah.
So there exists some polynomial that satisfies this condition with a degree less than or equal to the number of points p. And that's because we consider I'll use this notation. Okay.
That was like some sort of diagonalization thing.
Yeah.
Gotcha.
And
Nice.
so on. Okay. But can we beat p? The surprising answer, I guess this isn't that surprising, but we can. We can destroy p. So the way we're going to do this is, let's try to leave this here. Okay. So we're going to consider the vector space of polynomials with degree at most p over R. And we're going to consider the following map from V of D to, what is this? It should be x to the p. Sorry, R to the p. So not R to the k, and this is a little subtle. So what this map does is you plug in a polynomial of degree most d, so it goes from this, and then it spits out the p tuple of points. That's just what you get when you plug in the first point, the second point, and so on. Okay. And so this map is a linear map. Because if you have P1 plus P2 evaluated at a specific point, it's the same as adding them, and then yeah, it makes sense. So by linear algebra, if this is true, if that's true, then there should be a non-trivial kernel to this map. And the kernel of this map is just a polynomial that if you plug in every point you get 0, which means it's a polynomial that satisfies our condition. So this now we just have to compute the dimensions of these two vector spaces. And so what's the dimension of R to the D? Okay. And then the dimension of V of D, that's like combinatorics problem. I don't want to do that. I probably won't. But the idea is that the basis is like things like this. It's K? Yeah, it's K. Okay. So these are all the bases. And you can do, I think, stars and bars. But it gets you this. The dimension is, and then, okay, I'll just believe it. And then this is approximately equal to d to the k over k factorial for if, and that's kind of subtle. That's if we're fixing d. Sorry, no. We're fixing k because we want to stay in a specific dimension, but we're making d be large because we want to consider sets with lots of points. And so for that, when that's true, then this approximation is pretty good. Okay, and so now we're left with the inequality d to the k, and I'm sorry that I'm jumping around. Okay. D to the k over k factorial is greater than or equal to, no, it's strictly greater than p. So the degree is p k factorial times p no, that looks really good. Yeah, that's fair. All right. P times k factorial to 1 over k. So very small, because we had an approximation that was less than or equal to p here, but this is like p to the 1 over dimension, which is very small. Okay. So what? This does not seem immediately relevant to any kind of distance geometry problem, because what am I going to do with one? It turns out that it is. Some of these arguments get very involved. The one I'm doing today is not. But there are like very complicated ways to use these that do really cool things. So one of the problems that people use it for is called the Erdős. Just as an example of an application, the Erdős distinct distance problem. And so that's a question in the plane. If you have a bunch of points in the plane, it's very easy to position them such that each of the n choose 2 distances is distinct, right? That's pretty easy. But it's kind of hard to position them so that most of the distances are the same. It's not obvious. And so you can use the polynomial method, don't ask me how, to get this bound on the number of distinct distances, and which is something that you can't do without it. Like the best bound without it is like something like that. So,
And you best believe to be best possible?
this is not okay. If you put the best possible configuration people think is if you put all the points into
Squares.
into a square, and then you can do some analytic number theory, and you get that. And people think that this is the best, so this is almost.
This close.
Yeah, it's close. Okay, but we're not going to use it for that. We're going to do something simple. All right. So the proof for the upper bound, that's what I'm doing there. Upper bound on the joints problem. Cool. We're going to show that given n lines, you can create at most n to the 3 halves joints times some constant factor. And so first we're going to introduce a lemma, and I'm going to try to use the word a little better.
Maybe you can use it if you want to go.
Oh, that would help.
Yeah,
why don't
just-
I do that?
yeah.
So I keep this lower bound here. Okay. So we have L lines and J joints. And they're in some configuration. So we're going to prove that there exists some line with, at most, this many joints on it. And this already looks familiar because of this. Because when k equals 3, which is the dimension we want, that is that. So that's where that comes from, and that's what we're going to apply. But basically, the way we'll approach this proof, we'll show that there must be some line with not that many joints on it. And so then we're going to take it away, we're going to get a new configuration. And by this lemma, there's still going to be another line with not that many joints. So we're going to take them all away one by one, and at the end, we didn't take away that many joints because we couldn't have, but they're all gone. So we can, like, induction. Okay. So, prove this. We suppose otherwise. So, suppose otherwise. And now we consider some polynomial. So this would, I guess, be a 3-variate polynomial that vanishes on every joint. So let P vanish over the joints. So the degree of P is going to be, by our theorem, is going to be at most, or we can find such P such that the degree is at most that. Now, there's a fact about polynomials, and that is if you have a polynomial on a line and it vanishes at a lot of points and it has a small degree, then it doesn't work. Basically, if it vanishes on k plus 1 points and it has degree k, then it must just be the zero polynomial on that line anyway. So if P vanishes over the Ji and it has fewer than this many, its degree is less than this, so it can't vanish more than this number of times on each line. But we're supposing otherwise, so we're supposing that each line has more than that number of joints. So that means that P has to vanish on every line. Okay, so P vanishes on the lines. Now, if P vanishes on the lines, then we will consider multivariable calculus. We have a joint here, and we've been told that P vanishes on each of these 3 lines. So that means its directional derivatives on each of the 3 lines is 0. And since its 3 directional derivatives are all 0 at this point, and together they span the space, because that was one of our conditions, then that means it's all of its derivatives must be 0 at this point. So just say its derivative with respect to x must vanish at this point. And we can do this for every single joint, and we get that the derivative vanishes on all the joints. Okay. Now, if the derivative vanishes on the joints, then we've produced a polynomial with less degree that vanishes at every point. But we were already choosing the minimal polynomial, so there's contradiction. And that means that this lemma must be. Okay, cool. So we got that lemma, and now it's pretty easy. Okay. So given this, we have a number of lines. And each line has at most 6 j's and 1/3 points. So that means that the joints per line is at most 6j 1/3. Okay? And so you solve this equation. I don't want to do the algebra. I guess I'll do the algebra. Solve equations. Let's say j to the 2/3 over 6 to the 1/3 is that right? Seems legit. Okay. So now we take both sides to the 3/2. And we get j over square root of 6 is less than or equal to L to 3/2. And so we prove the joints there. Okay. Now, what's funny about this argument is that we're counting each of the lines equally. So we said that there exists some line with at most 6j to the 1/3. So we can imagine if we have a graph, lines removed, and we have like joints per line. Then it starts, we know that the upper bound is that. Okay. And so we kind of have, at each step we remove, so we have some like, it looks something like this, right? And what I'm graphing is, by the way, at each step we take out the line, delete all the joints associated with that line, and we get a new construction, and now it has a different number of joints. And this is the joints per line on the line with fewest joints. Now what our bound is, and of course we can bound this by this times this. So if this is like L, then the number of joints is of course less than or equal to L times 6j 1/3. But as we go along, this becomes a stricter and stricter condition. So I'm not being very clear. But basically the idea is that if we start off with 1,000 joints, then this says that there must be a line with the most like 10 times 6 to the 1/3 joints, so like a small number of joints. But when we get down to, when we start removing lines, I said joints. Did I? No, I think I meant joints. If we have lots of joints, then there's a line with like 10 or 11 joints on it. But as you remove 1,000 down to like 100, then there's only a line with like 6 joints on it. But this like induction is still using the weaker bound of 11. So what we can do instead is we can sort of introduce a new method to bound this sequence, which is something that's kind of nice. So to think about this abstractly, imagine we have a sequence. What?
You can use this.
Oh yeah, that's probably stupid. That's fine. Okay, so if we think about this abstractly, let's suppose we have a sequence defined by the following rule. So for us, this is going to be the number of joints on a given line. The number of joints. At each step, we decrease by the number of joints we had in the previous configuration. We decrease it by this much. And this makes sense because we were allowed to decrease it by this much by that one. Okay. But just think about